We'd like to thank you for joining us as we spend a little bit of time to show you how Optimus can be coupled with ANSYS Workbench. And I think as you've begun to understand a little bit about Optimus, I think you'll be able to clearly see many of the advantages that Optimus has. My name's Taylor Newell. I'm an application engineer with Noesis Solutions. So as we show you a few case studies today, we'd like to point out that some of the features of Optimus, when combined with ANSYS Workbench, are extremely easy to use. In a short amount of time, you're able to automate a workflow that you can then drive a repeated automated process. You can instantly integrate with fully parameterized ANSYS models, or interface with fully parameterized ANSYS models. And after the workflow is set up, really it's one click in order to run baseline, in order to set up and run DOE or large optimizations. Optimus is extremely efficient. You're able to identify key design parameters in your design space. Optimus incorporates some very cutting-edge, intelligent optimization methods that allows you to arrive at optimal solutions in a very short amount of time. With all of that, Optimus also allows you to interface with any of your HPC resources, both Windows and Linux. And Optimus has a number of robust assessment and analysis tools that give the user the ability to very quickly perform complex robustness analyses. So we'd like to point out these features with two case studies that we'll show you today. The first is the optimization of a support bracket for a cable tray that you can see there in the upper right. The second is an aerodynamic optimization of an F1 rear wing. And the interesting thing about this case, as you'll see, is that we actually are able to optimize over a range of speeds. And we do a robustness analysis. So for the first case study, it's the optimization of a support bracket. This support is statically loaded by a cable tray. We want to ultimately reduce the mass of the bracket while still ensuring that the bracket can withstand the loads that are placed upon it. Here you can see the model design space with the nominal case sitting right about in the middle of this design space. You, on the left side of the screen, can see the model first in CAD and then in Design Modeler. We will be working with about 10 design parameters, both geometry parameters and a few material properties. There are two goals of the optimization. We found that the baseline case had an extremely high maximum stress of about 933 megapascals. The first goal of the optimization is to reduce that maximum stress below 350 megapascals. And after that constraint or objective is met, we want to reduce or to minimize the mass of the overall design. For the baseline case, the mass is about 0.29 kilograms. And as I mentioned before, the maximum stress is much higher than the constraint at 933 megapascals. So the first step in setting up this optimization, of course, is to set up the workflow inside of ANSYS Workbench. Here you can see here you can see that ANSYS has identified the geometry and design modeler, and then that is fed into the static structural analysis. The parameters that are part of our design space have been identified and are exposed as part of the parameter set. The workflow inside of Optimus is actually shown here on the screen, where we have the input parameters on the far left, the simulation and the input and output decks in the center, and then the output parameters on the right. And here you can actually see the user interface of Optimus. Optimus is an extremely easy to use tool with all of the functionality being exposed to the user from the primary GUI interface. So here you can see some of the methods such as design of experiments and optimization on the top, some of the interfaces that allow Optimus to interact with not just ANSYS but many other tools, including in-house tools and common tools such as Excel and Python. And then on the left you see some post-processing options. Here you see the dialog boxes which Optimus has that allow you to interact with the ANSYS Workbench project. On the left you see the input dialog box, and you'll notice that ANSYS automatically detects the parameter set inside of ANSYS Workbench. The center dialog is used to actually call and run the analysis, and then the far right dialog box is used to identify the output parameters. It is important to note here that Optimus is in fact making changes to the Workbench project and creating or writing out a new Workbench project every iteration. So the optimization strategy that we will use is first we will create a design of experiments. After we have that information, we will use it to create a mathematical approximation of the design space. This mathematical approximation is typically referred to as a response surface model. That response surface model is essentially a mathematical formula, and we can then run the optimization on that mathematical formula to run a very large optimization very quickly. After we have a result, because that optimization was run on this response surface model, there is a little bit of error, and so we'll want to run a local optimization on the analysis model, so back inside of ANSYS directly. And that, of course, will lead to our goal. So the first step in that strategy is to perform a design of experiments. We combined a full factorial design of experiments with a Latin hypercube to ensure that we've covered the entire design space. And here you can see the results of that design of experiments. You'll notice right away the baseline being the green triangle, and then the constraint value being the green bar to the left side of the graph. In the entire design of experiments, only a few designs actually satisfied the constraint. The correlation analysis gives us a little more insight into the design space. In fact, we find that the surface body thickness is the most important parameter out of all of the variables. Now that the design of experiments is complete, we can actually generate this mathematical approximation, this response surface model on the entire design space. We're able to select different response surface models based on the error that that mathematical approximation had. So we select the best response surface model for each individual output. Next, we run a large global optimization using that response surface model. This allows us to run many hundreds of experiments in just a matter of seconds. We ran the optimization, and as you can see the results on the right there, we were able to satisfy our constraint, and of course the trade-off was that we did increase the mass. So after the global optimization, we reduced the maximum stress by about 62% and only increased the mass by about 13%. At this stage, we're ready to begin a local optimization on the analysis model itself. So actually going back and forth from with ANSYS Workbench. As we mentioned before, there will be some error between the response surface approximation and the analysis. After this optimization, we arrived at the results that you can see on your screen. We were able to minimize the equivalent stress down to 329 megapascals, and also minimize the mass to about 0.32 kilograms. And here you can see the progression of our optimization strategy, starting from the green triangle and ending up at the Optimus logo. And here are the results of the geometry itself. On the left image you can see the baseline or the initial design, and on the right image you have the final design. With a very small increase in mass, we were able to significantly decrease the maximum stress. Now the next stage is to perform a robustness and reliability analysis on the information, on the data. In order to do this, we apply a probabilistic distribution to each of the input parameters. As you can see here, we've applied a 2% range to each of the inputs, and you can see how this affects the thickness and how this affects the height. We specify a normal distribution for both of these values, with the nominal value being the result of the local optimization. And what we find on the bracket is that we have, out of 1,500 designs that were run, we have only a few that were failure modes. In fact, we ended up with about a 0.23% failure probability. And perhaps what's even more important is that we simply specify, if we specify that the surface body thickness must be above 1.94, we will have a 100% reliability rating. So what's the impact of all of this? If someone was to perform this optimization in a traditional sense, we've estimated that it would take about 10,000 minutes. Frankly, it would be impractical to perform. But with Optimus, this entire process could be done in a little less than 10 hours. So we hope that you've been able to see with this first case study that Optimus was able to perform, or that we were able to perform, a successful optimization of this cable tray. We were able to utilize some efficient optimization strategies as part of this. The next case study is an aerodynamic optimization performed on a rear wing of a race car. It's performed over various vehicle speeds, over multiple vehicle speeds. In order to optimize the aerodynamics, or I guess when we say that we want to optimize the aerodynamics for this wing, we want to maximize the downforce to drag ratio of the wing itself. And we also want to minimize the deflection that the wing and the flap encounter. This, of course, requires a one-way fluid structure interaction. And combining Optimus with ANSYS Workbench makes this very easy to set up and ultimately to run. Inside of Workbench, it's very easy to parameterize the entire process, from importing the CAD model to automated meshing, solving it inside of Fluent, and then performing the post-processing. With Optimus, we're able to wrap ANSYS Workbench and actually drive the decision making as part of this process. The design parameters that we're going to be looking at, so the input parameters that we will be making changes to, are relatively simple here. There are three parameters. One is the angle of the wing, the second is the angle of the flap, and the third is the wing translation in the horizontal direction. In addition, we'll be looking at three separate air velocities, 42 meters per second, 56 meters per second, and 69 meters per second. Here's an example view of the simulation results. the vertical force that we end up with is down force. The horizontal force is drag. We take that ratio. And then we also, so that's all done from the CFD, or the fluid side. And then on the structural side, we look at the maximum total deformation of the wing, of the flap. The pressure loads from the CFD are transferred as boundary conditions to the structural model inside of ANSYS Workbench, as you can see here. As I mentioned before, we want to maximize that downforce to drag ratio, and we will actually place a constraint on the maximum total deformation. So we recognize that some deformation will occur, but we'll specify the maximum value for that deformation. And then we want to find the optimal wing configuration for multiple vehicle speeds. This will require, inside of Optimus, a multiple level workflow. The higher level will be the optimization of the 3 parameters, and then the lower level will be the running of those parameters at 3 separate speeds. And here you can see that multi-level workflow inside of Optimus. So in the top level, you see flap and wing angle along with the wing X translation. And then we receive, or we extract, a number of responses out of that. And on the lower level, this is where we actually call ANSYS. We pass along the angle for the wing and velocity, and we run a table of these 3 separate speeds. The lift to drag ratio and deflection are then passed along to the higher level. Our optimization strategy will be the same that we used for the previous case study. We'll start by creating a design of experiments, then use that information to define a mathematical approximation or response surface model, then run a global optimization on that response surface model, and finally verify that optimum. Here, the design of experiment, because of the long runtime of the CFD, we've actually truncated the design of experiments a little bit. We're only doing 45 CFD runs using a Latin hypercube DOE. Because of the automation that Optimus has used, we've reduced the need to manually open and reclose these files and to do all of the remeshing. In addition to all of that, we've set ANSYS to run in parallel, so all of these things run, all of these models in the DOE run simultaneously. Here, we actually show the Sobol indices, which of course tell us the influence that each of the individual input parameters have on the output parameters. And here we see that the flap angle corresponds very highly with the deformation. The wing angle has a high correspondence with the downforce to drag ratio. And the wing horizontal translation influences mostly the maximum equivalent stress, which is not necessarily considered in this optimization. We are also able to use an advanced post-processing tool called a self-organizing map to gain a very quick understanding of our design space. The self-organizing map arranges the designs in ways that correspond to secondary parameters or additional parameters. So here you can see that because the low values, or the blue values, for both flap angle and maximum total deformation are located in approximately the same position, we know that those 2 parameters are highly correlated. And of course, the Sobol indices that we saw in the previous slide confirm that. So now we run a global optimization on the response surface model that was created from that DOE. We're attempting to maximize the downforce to drag ratio while constraining the deflection. We use a optimization algorithm known as a self-adaptive evolution, and the results you can see are actually quite good. and you can see them on the graph on the right side of your screen. The results, of course, are that we reduce the deflection by about 20% while increasing the the downforce to drag ratio by about 20% as well. Now the next step is to perform a robustness and reliability assessment. We apply the same 2% parameter drift to each of our input parameters, and what we quickly find is that there's a 46% failure probability in this probabilistic distribution of our input parameters. So these are designs that had a very high deflection. So by applying an optimization for 3 sigma, we find that our optimum moves slightly, as you can see in the design space on in the chart. We move from the border right along the edge of that failure region a bit further away from the region. Of course, this does affect our performance. So we initially had about a 20% increase in downforce to drag ratio, but with the robust and reliable optimum, we only have about a 17% increase in downforce to drag ratio. The trade-off, or the advantage that we do gain, though, of course, is that we have a larger reduction in the deflection. And here you can see the corresponding results. So in conclusion, we were able to, with this case, show an integration with ANSYS Workbench that was performing a fluid structure interaction. We used a design of experiments and a response surface model to do an optimization on a computationally expensive CFD simulation, and then we were able to drive a multiple level optimization that allowed us to optimize for multiple air velocities, or vehicle speeds. In summary, as we've gone through both of these case studies, I hope that you've been able to see that combining Optimus with ANSYS Workbench is extremely easy to use. It takes a limited amount of time and of user interaction in order to automate and fully parameterize these models. It's an efficient tool to use. You're able to gain a deep understanding of your entire design space very quickly, and you're able to apply cutting-edge optimization technology to your design space. And then finally, Optimus gives you the ability to perform robustness assessments and reliability optimizations. We'd like to thank you for your time. If you have any further questions, feel free to send us an email or check out our website.